If you rely on a generator to keep your refrigerator cold during an outage, you're burning fuel to solve a problem hardware can fix. A standard 3 kVA generator consumes roughly 1.2 liters of fuel per hour. Run that for 8 hours a day, and you're looking at over 238,000 naira a month in fuel alone, plus another 20,000 to 30,000 for oil changes and spark plugs. Transitioning to a battery and inverter system eliminates the fuel and the noise. The math heavily favors the inverter over the long term, but making the switch introduces a sizing trap that catches almost everyone off guard. The mistake happens when you check the sticker on the back of your fridge. You see it draws 200 watts, so you buy a 500-watt inverter, assuming you have plenty of headroom. Generators sit here, cheap to buy, but expensive to run monthly. Blindly migrating to an inverter without understanding power draw means buying massive batteries just to prevent compressor stalls. Your goal is this bottom left quadrant, a perfectly matched system keeping upfront and monthly costs low. Moving to battery backup is a financial necessity, but guessing the size of your equipment will either plunge you into immediate power failure or cost you hundreds of thousands in unnecessary hardware. To get the sizing right, you have to look at the physical mechanics of a traditional refrigerator. The real challenge has nothing to do with keeping the fridge running. It's entirely about breaking it out of a resting state. The fridge's compressor motor is heavy. Forcing that dead weight to start moving and push refrigerant demands intense energy to overcome physical inertia. To get moving, that motor pulls 3 to 5 times its normal running current. Your fridge might only need 200 watts to run smoothly, but when the cooling cycle starts, demand violently spikes to 1,000 watts for 3 seconds. When that 1,000 watt spike hits a 500 watt inverter, the system reaches its breaking point instantly. The inverter's internal safety mechanisms trigger a protective shutdown. The entire system trips. Your batteries are completely full, but your food is still getting warm. Buying an inverter for a traditional fridge is a battle of surviving a 3-second startup surge. The running wattage doesn't matter if the compressor can't turn on. Let's assume you want to avoid the appliance store entirely and run your existing 200-liter traditional fridge on a new backup system. To guarantee the inverter survives that 1,000-watt surge without tripping, you are forced to purchase a unit rated for at least 2 to 2.5 kVA. This matrix breaks down the hardware requirements. Because traditional fridges operate on heavy duty cycles, keeping that appliance running for a full 24 hours demands a massive 400 amp hour battery bank. Facing that massive hardware cost, many people try to save cash by purchasing a cheaper, modified sine wave inverter. This split-screen diagram illustrates why that fails. Grid electricity is a smooth, continuous curve, like the pure sine wave on the bottom. Modified inverters produce the jagged, stepped power wave on the top. When you feed a compressor those sharp, blocky electrical pulses, the motor is forced to fight itself. The physical result is intense internal friction and violent vibration. The compressor runs dangerously hot, consumes extra power, and will eventually burn out entirely. Keeping the old appliance means avoiding an upfront purchase at the store, but you pay for it by buying oversized batteries and a premium pure sine wave inverter just to keep the old motor alive. The alternative is treating the appliance itself as the solution to the surge problem. Modern inverter fridges operate using variable speed compressor technology. Instead of treating cooling as a harsh on or off switch, the motor continuously adjusts its speed to match the temperature demand. When the compressor kicks in, it draws power through a slow, gentle ramp-up. There is no violent spike against mechanical inertia. Instead of pulling 5 times its running current, an inverter fridge rarely demands more than 150 to 200% of its baseline power at startup. Looking at this comparison matrix, the absence of that massive surge changes the math entirely. The mandatory inverter size instantly drops from a 2.5 kVA unit down to a modest 1 to 1.5 kVA model. Because the variable speed motor continuously maintains the cold with remarkable efficiency, your battery requirements plummet. A 24-hour backup cycle now only requires 200 amp hours, exactly half the battery storage of a traditional setup. The checkout price of the new appliance allows you to purchase a significantly smaller, cheaper backup power system, neutralizing the upfront cost of the fridge. Securing your backup power ultimately comes down to a strict mathematical equation. You either upgrade the appliance hardware right now, or you commit to buying larger batteries for the life of the system. This flowchart breaks down your exact next steps. It starts with one question. Do you need a new fridge? If the answer is no, and you are running a standard 200-liter model, your shopping list is strict. You need a 2.5 kVA inverter and a 400 amp-hour battery bank to handle the duty cycle. And you must ensure the inverter specifies pure sine wave output, or you risk destroying the compressor. If the answer is yes, you purchase an inverter fridge. Because the variable speed compressor eliminates the startup surge, you only need a 1.5 kVA inverter and a 200 amp-hour battery. Factoring in the cost of the appliance against the cheaper hardware requirements, you save roughly 204,000 naira on the total system cost by taking the upgrade path. Because the fridge demands so little continuous power, you retain plenty of available electrical capacity to run your lights, fans, and charge your phone simultaneously. An inverter can absolutely carry a fridge. But the smartest financial move is ensuring your appliance meets the power source halfway, utilizing modern efficiency to keep your total investment exactly where it belongs.